Forni and Matthews. Okay, I will write larger. Okay. Anyhow, Giovanni, Forni, and Matthews. That's easy. And but in order to talk about this, there will be I will need to speak a little bit of also of previous work which was made with Pierre Moussat and Jean-Christophe Yoko. Okay, so it will be much more a dynamics talk than a Teichmüller one, so I apologize. And it will be a talk which goes to the heart of some problems of dynamics which are normally called as stability of quasi-periodic orbits. So the idea is that somehow there is a large portion of dynamical systems which are relatively well understood. And these are quasi-periodic systems, and they have some property of stability, which is some, in a nutshell, the content of what is called KM theory. And the prototype of this behavior is given by the rotations, Diophantine rotations on the circle. And the idea here, as you will see, is a little bit to extend the theory from the circle to general interval exchange transformations. So in order to explain a little bit better what we do, let me start from recalling you just a second what I mean by Diophantine. So in a second, I mean, later I will define a Diophantine interval exchange transformation, but for the moment I just consider an irrational number. So I have its continued fraction expansion. Let's say that we take it to between 0 and 1. So which is 1 over A1 plus 1 over A2 and so on. Okay, so and I denote with pk over qk the truncation ad order k of the continued fraction. And then, I mean, I say that alpha is just Diophantine if ak plus 1 is big O of qk of some power tau for some tau. I mean, if there exists tau greater or equal than 0, such that this is 2. And there is a special class inside of this which are called Ross-type numbers. And for Ross-type numbers, you ask the same, but you ask it for all tau which are strictly positive. And so this is the same. This definition here is the same as asking that alpha minus p over q is bounded by gamma 2 over q to 2 plus tau for all rational numbers p over q. So I mean the statement is that for all tau positive there exists a positive constant gamma tau, and these are called Ross-type numbers because of Roth theorem, 1955, which says that if alpha is algebraic, then alpha is of Roth type. But of course, the set of Roth type numbers is much bigger. In particular, it has full Lebesgue measure, which is, yeah, of course, it's the other way. Yes, thank you. Okay, so Diophantine numbers have this property that somehow the rational approximations are controlled polynomially, and Roth type have somehow the lowest possible rate of polynomial growth, which is just a little bit, I mean, on the other end, I mean, of quadratic irrationalities. And then the idea is that the goal will be to generalize this notion of Diophantine and of Roth type numbers to interval exchange transformations. So let me just remind you that an interval exchange transformation is obtained, of course, I mean, when d is equal to 2, it includes the case of rotations. I mean, so you just 1 minus alpha here, and you have AB, BA. And then so where, I mean, if I normalize the length to be 1, the case of the irrational rotation is encoded in a two-interval exchange transformation. In general, if you want to go from genus 1 to higher genus, you need at least 4 intervals. CVA. And so they're determined by a couple of data. You need the length of the intervals and some combinatorial data. The combinatorial data is trivial in the case of d equal 2, but it becomes quickly non-trivial as soon as you have 3 or more intervals. And then so the dictionary is that for d equal to 2, a standard interval exchange transformation, so on each interval you just have the translation, you just translate the intervals, correspond to rotations by alpha on T1, and so alpha of x is x plus alpha. And here you will have a different map, which is a piecewise translation. And there is also the possibility, and we will do it, of talking about generalized interval exchange transformations. And then when you come to generalized interval exchange transformations, you just replace the assumption that you have piecewise translations by assuming, so you fix some regularity. So you fix some R, which is at least 0. And you replace the assumption of having piecewise translations by the assumption of having piecewise CR diffeos. So the restriction of the map to each of the intervals should be, to the closure of each of the intervals should be a CR diffeo. Okay, so these are piecewise CR diffeos. Okay, so, and the correspondence here in the case d equal 2 is exactly with the orientation preserving CR diffeos of the circle. So the point of view that we want to adopt, that we have been adopting in all these years, so the point of view is the following, is that we look at interval exchange transformations or generalized interval exchange transformations as a multi-frequency but still one-dimensional extension of circle. Well, if it is a generalized IET, it's we are talking about circle diffeos, and otherwise of circle rotations. So the idea is connecting with the first sentence of my talk. The idea is that you want somehow to extend the theory of quasi-periodic motions and the stability of these quasi-periodic motions from the case where you just have one frequency, the rotation number alpha, to the case where you have several frequencies, but without going to a higher dimension. Okay? And this will be crucial also in the tools that we use, because at some point, very soon, we will talk about the Schwarzschild derivative, and this is a tool which is absolutely one-dimensional and not higher dimensional. Of course, there is the possibility of generalizing by going to higher dimension, but that is a different business, and it also leads to completely different arithmetical problems, which are in some sense simpler, because, I mean, if you want to talk about KM theory for flows on higher dimensional tori, that is not difficult to do, to show the theorem. But at the same time, if you aim, as we are very far from that, but if you have in sight, at least asymptotically, the possibility of getting optimal conditions, which was one of the motivations, which is still very, very, very far from being realistic, then perhaps the multi-frequency but one-dimensional case looks a little bit less desperate. Okay, so in general, the problem we want to address and that we have to explain a little bit is the problem of, so the problem is the problem of conjugation of a generalized IET T to a standard one. And of course, we will assume that assuming T close to T naught. Okay, so what is normally called the local case. Okay. Okay. Oh. So this will lead us, I mean, those who were here in the past 2 weeks, I mean, 2 weeks ago, no, last week actually, had the opportunity of following Giovanni's lectures on the cohomological equation. And I'm not sure if he mentioned it, I looked a little bit to the lecture, I missed them. I'm not sure if he mentioned it, the conjugacy problem as one of the sources of the cohomological equation. But this is what we will see now in action. Okay, so the cohomological equation, which is basically the second simplest equation you can ask to observables on a dynamical system. The first one is, of course, the question of invariance. I mean, looking for first integrals. So you look at the variation of an observable along one step of your dynamics, and if it's constant, you call it a first integral. This is normally what we don't want, because we want to talk with, we want to work with ergodic systems. Otherwise, the dynamics is basically reducible. The second simplest question that you can ask is to find, prescribing the variation of a function, find an observable which has the desired variation along one step. So this is what you get from linearization of the conjugacy. So this leads to the cohomological equation. So if you simply look at the conjugacy equation, which I didn't write, okay. So the idea is that you have T, and you look for a change of coordinates which maps your T to T naught. So T would be a generalized interval exchange transformation. You can think of a map of the circle, of a circle differ if you want, maybe close to a rotation. And T0 would be a standard interval exchange transformation, or just a rotation. Then, if you just assume T to be a perturbation of a standard transformation, I mean, just a slight deformation, then you can, of course, if you had T naught, then there would be an obvious solution, which would be the identity. So you can look for H in the form identity plus delta H. And then you can plug and substitute and write what you get. And of course, you get neglecting higher order terms. And the linearization, just the first order terms, become delta H after T naught minus delta H equal to delta T, which is exactly the cohomological equation. So this is, of course, the basis for understanding a little bit what is going on. In the case, let me just write because it will be useful in a second. in the case of the circle, I mean, on S1, if we assume T naught just to be a rotation by an angle alpha, then you simply get the equation delta H of x plus alpha minus delta H of x, which is equal to delta T of x. Okay? This is just a super simple equation that we will discuss in a moment in terms of Fourier analysis, very easily. There is also another possibility of getting the cohomological equation in a slightly more sophisticated way from the problem of conjugacy, and which is exploiting what is called the Hermann's-Schwarzen derivative trick. So this is based on a paper of Hermann on the bulletin of the Brazilian Mathematical Society in 1985, which is a little gem. I'm absolutely grateful for this paper because it has been supporting at least the last 15 years of my research activity. I mean, it's just 20 pages, but if you dig and dig and dig, you find sufficiently many gems to be able to keep working. And well, Hermann had a very different motivation, which was related to a very exotic question asked by Kolmogorov and unsuccessfully investigated by Arnold on the monogenic character of the solutions of KM problems. So that was a very strange thing. But anyhow, Hermann had the idea that one can try to solve the linearization problem, which it was, of course, treated until then basically by iterating some sort of Newton method, which is at the heart of KM. So by by solving an equation of this kind infinitely many times and then building one piece after the other, the solution of your linearization problem by successive better and better approximations, just in one step by a fixed point argument. So the idea is you take the Schwarzen derivative, S. So in general, if you have an interval map, S of f will be d squared log df minus 1/2 d log df squared. And okay, so the Schwarzen derivative has the property of vanishing if and only if f is Möbius. Okay, and it also has a chain rule. Okay, which also has S of f composed with g equal to S of f composed with g dg squared plus S of g. Okay, so as long as you look at rotations or standard interval exchange transformations, the target, I mean, T naught will be in the kernel of the Schwarzen derivative. So, and by the way, this means that if you start close as here to a standard interval exchange transformation, the Schwarzen derivative is expected somehow to be small of your transformation. And if you apply the Schwarzen derivative to the conjugacy equation, what you get, so apply conjugacy equation, what you get is the following. You get S of t composed with h. Sorry. Just want to get to the result, otherwise it's a little bit long. S of h composed T naught minus S of h equal to S of t composed with h dh squared. This is just the result of applying the chain rule to the conjugacy equation, which is here. And recalling that S of t naught is 0 and that the derivative of T naught is identically equal to 1. Okay? So when you apply the chain rule, you just have to keep in mind these two things. And then you naturally get to this equation. So what is the form of this equation? So on the left-hand side, you have the same structure of the left-hand side of the cohomological equation. You have the variation of the Schwarzschild derivative along one application of the standard interval exchange transformation T naught. Okay? So you just have the variation of SH. And on the right-hand side, you have something which is a little bit more complicated, but not extremely more complicated. It's, of course, not a given function, okay? Because you have h also at the right-hand side. But the interesting part of this is that it depends. Here, on the left-hand side, you have something which depends on h through the Schwarzschild derivative. So basically, it depends on the third derivative of h. But on the right-hand side, you have something which only depends on h through the first derivative. So there is a sort of imbalance between the right-hand side and the left-hand side. Because if you try to think about this equation in terms of, I mean, a little bit naively, the idea is that, and you want to apply a fixed point argument. So the fixed point argument would be something like saying, that, so first of all, of course, if you look at the right-hand side and you call it phi of th, the good news, of course, is phi of T naught identity is 0. Okay, so this is very important. So I mean, if you start from, if you apply this to the identity and the standard transformation, you have a 0. So as long as you ask yourself to be close to the standard interval exchange transformation, you have a hope of this being small. And then, if you look at it, what you in principle want to do is the following thing. You want to look at h as what? Well, s minus 1 composed with inversion of cohomological operator composed with phi. Okay? So this is what you want to do. You want to look at the fixed point of this transformation. And what I'm saying is that at the very end of your chain of composition, you have a very regularizing operator because you're taking 3 primitives. So here you gain 3 derivatives. Here, a priori, what you know is that you have something which depends on the first derivative. So you're losing one derivative. So if you want to have a fixed point, you need to start and get to the same space. If this inversion were something friendly, then you would have already be finished. I mean, there would be no problem. I mean, if there were no problem in the inversion of the cohomological equation, I wouldn't be giving this talk on one side, and on the other side, the proof of fixed point would be totally trivial. But there are, of course, problems. But you have a little bit of room for adjusting, because basically you have the possibility of controlling everything as long as in the process of solving the cohomological equation, you don't lose more than 2 derivatives. Okay? So this is basically the idea. Let's see very quickly how it works on the circle, and so that we get a little bit more of a grasp. So if we go back to the equation on the circle here, and we look at what happens on the Fourier coefficients, what you get is delta h hat of k. So now k is in z, and I denote delta h of x as the sum of delta h hat of k e to the 2 pi I kx, k in z, different from 0, times e to the 2 pi I k alpha minus 1 equal to delta t h of k. So you can obtain the Fourier coefficients of your unknown function just by dividing those of the given function by something which is the exponential of 2 pi I k alpha minus 1. On the other hand, this is either you k alpha, the fractional part of k alpha is substantial, and then this is basically nothing. I mean, you divide by a number. Or k is one of the good approximations of alpha. When it's one of the good approximations of alpha, this is essentially a sinus, so it behaves like k alpha. Okay, so in this case, you control it with k alpha. And then, of course, this is just saying something like k alpha minus n. And if we go back to our characterization of Diophantine numbers, well, it was written not with, you have to multiply by q. But basically what you see is that if alpha, so circle, if alpha is Diophantine of exponent tau, then the inversion of the cohomological operator costs 1 plus tau derivatives. Okay? So as long as you keep tau smaller than 1, and you have the right to do it for a full measure set of numbers, because the Roth type, which is basically tau 0 plus, is a full measure, you can make this thing work. And this is basically what Hermann did in his paper in 1985. Okay? Okay, now, from now on, we have to discuss interval exchange transformations with more than 2 intervals, because otherwise I will be stoned before the end of the talk, and define what we mean, what we want to call Diophantine interval exchange transformation. We actually have to do more than this, because first of all, we have to, given a generalized interval exchange transformation T, I have to tell you how to choose T naught. Okay? Because on the circle, there is a natural invariant, which is the rotation number, which is basically, when you have a map of the circle, the average speed of rotation under the iteration of your map. We have to find the analog of the rotation number, which is, as you will see, an invariant by conjugacy, so that to know, given T, what T naught we want to use. Of course, if we have in mind from the beginning that T is just a deformation of T naught, this is less of a problem. But still, we have to discuss this. OK. So the tool, well, I shouldn't have, OK, well, that's life. The tool that provides at the same time good, I mean, the information which generalizes the continued fraction expansion to interval exchange transformations and the notion of rotation number is Rosy-Veach induction and its acceleration in various ways. I mean, we will use a convention which has been introduced by Jean-Christophe. And so the idea is, well, I mean, I think I don't need to, let me just briefly recall the Veach induction. So the real novelty for you will be that it generalizes also to nonlinear interval exchange transformations. Okay, so you can generalize the Rosy-Veach induction to nonlinear interval exchange transformations with basically no pain. In the case we want to consider where generalized interval exchange transformations are thought to be close to standard ones, we may even assume that generalized map to be on each interval compactly supported in such a way that you don't touch what the behavior at the discontinuities of your map. And then in this case, the partitions before and after applying your map are the same. And then it's really clear that there is no problem in generalizing the Rosy-Veach induction. So the idea, of course, is that when you come to this, you compare the length of the last interval. So what you do is actually inducing, in this case, which is a top situation, you're inducing on a shorter interval. So you start from T, and you go to T hat. You start from a certain permutation P, and you will get a new permutation P hat, because T hat is going to be equal to either T if applied to a point which doesn't belong to the loser, and otherwise it will be t squared, because the point which stays in the loser, I call loser the shorter of the two intervals I'm comparing in the last position, and winner the longer. And in this case, you have to iterate once more in order to go back to the interval. So if you x belongs to A, so here you have your permutation, which is A, B, C, D, B, C, B, A. Here you have A, B, C, D, B, A, C, B. Yes, in this case. So this and the length data, if I denote with lambda the vector of the length of the intervals, change in the sense that the only change you get is for the winner, which is shortened, and it is and it is shortened precisely by an amount which is equal to the length of the loser. Okay. So this means that if you want to represent the behavior of the length under your transformation, you get a map, a linear map with a matrix which is the identity plus a single non-zero element outside of the diagonal, which is in the position I always mixed up, but either it is loser or winner or the other way around. Okay, so the notion of irrationality. I started, the first thing I said for talking about Diophantine was that I was talking about Diophantine irrational numbers. So the notion of irrationality for a standard is simply you just ask no connections. Also in the, which is what guarantees that you can iterate the Rosivich induction infinitely many times. And this has an important consequence in terms of iterating the Rosivich induction, because when you look at the Rosi diagram, associated in this case is well known. So you have arrows. And you can decorate this diagram by giving to each arrow the name of the winner. So in this case, you have a cycle of D and a cycle of A. And I think you have here B and C. And here it's mirror, C and B. Okay? So the fact that you can iterate infinitely many times the Rosivich induction says that starting here, this diagram here in the central position, this is the diagram corresponding to this permutation. To this permutation, actually. This is here, and this is the first movement where D is winning. We went from here to here. This is what I described before. So in this diagram, you get an infinite path. And the requirement that you ask is that this path has to be infinite complete, which means that each name, so the name is attached to the arrows. Okay? And it's just the name of the interval which is winning. So each name is taken infinitely many times. Okay? So this is what you require. Now, in the case, just to try to reconnect with more familiar things. Why is this a reasonable generalization of the continued fraction of an irrational number to the multi-frequency case? Okay, that was the point of view from the beginning. We want to look somehow at interval exchange transformations as generalization of rotations where you add frequencies. Okay, instead of having just one ratio between one length to another, you have in principle more than one. And in this case, you would have 4. Okay, so the reason is that if you just look in the case of D equal to 2, the diagram is very simple. You just have one possible permutation and 2 arrows. And the continued fraction is read by looking how many times consecutively you apply one of the two arrows. Okay, so unless you switch from one arrow to another here, from one letter to another, you have the same. You look at the length of iterates of A and B, and this will give you what are the partial quotients of the continued fraction. So this the idea is that alpha being A1, 0, A1, A2, and so on, reads in something like having a path which is A to the A1, B to the A2, A to the A3, and so on. I mean, something like this. And here, you could do the same. I think this is actually what Anton did in his first paper, where he proved the existence of a probability measure which is invariant under this acceleration of the Rosivich algorithm. But for our purposes, it's more convenient to follow a different acceleration, somehow to pack together more terms instead of just following the letters. And so the generalization of the continued fraction that we want to use is the one which follows Yukoth acceleration. And this has to do with the following packing of terms. So you introduce. So let me first of all introduce a little bit of notation. Let me say that if I start from an initial map and I iterate m times the Rosivich induction, I end up to a transformation which I denote with Tm. Okay, so m now is a non-negative integer, and so if I want, if I denote with bmn, so m less or equal less than n and bigger or equal than 0, the matrix which I obtain following a path in the Rosivich diagram which starts from the position of Tm and that's up in the position of Tn, and then taking the product for each arrow of these elementary matrices. Okay, so this is basically the product along gamma, which goes from the various gamma, which goes from Tm to Tn of the matrices B gamma. Okay, so these matrices have all non-negative entries. They are all ones on the diagonal, and somewhere outside of the diagonal 1. And we want the matrix to be positive. Okay, so we want to decompose the infinite path in chunks such that the transition matrix from one piece to the next has all the entries which are positive. Okay, so and this is your positive acceleration. So you start from actually from 0, and then you recursively define nk as the minimum of over n, such that b over nk minus 1n has all entries strictly positive. Okay. So this, for example, is a little bit different also from this. You need one more. I mean, even in the case of rotations, to get the same result, you should put together a to the a1 and the first to the b, but doesn't affect anything else. Okay. Okay. So in this way, these matrices will somehow play the role of our desired continuous fraction. And the dictionary to keep in mind relative to this is that the partial quotients will be replaced precisely by these transition matrices. So the idea is that, so a sort of dictionary. Or maybe I can take a little bit more room and try to make this thing more understandable. partial quotients. Yes?
So what, are there further accelerations? And
Yes. I mean, the point is that this is what is more than enough for our purposes. Actually, less than this would be enough. What is important is to have a little bit of control of how long it takes to get the entries positive. In this way, you know that you just jump on it, okay? But you have a decent combinatorial control because if you use another generalization of, which is the one we used at the beginning, and which is, by the way, not, I mean, quite natural, which is instead of jumping from one letter to another and packing together iterates of one letter, you make words which are maximal to the property of having all letters but one, which is, of course, as good as this one as a generalization of the d equal to 2 case. Then if you use that, you have an estimate. You know how many iterates of these accelerations are needed in order to get the matrix positive. You have an upper bound on the number of iterates. So in some sense, you can use several possibilities. What is useful is to have some control on how long it takes to get to this. And eventually, in this case, it's very simple. You just jump on it, and you don't need any estimate. Okay.
How big is this? Like, if you take a simple rosy diagram, how many matrices do you get?
I can answer you in terms of the other algorithm because the number of iterates, I think, grows with the number of intervals. Starting from the acceleration where you put all the letters but one. And on that, you have basically no control. Okay? Because, I mean, you can do, you can get stuck in one of these loops for a very, very long time. Then, of course, you have implicitly perhaps some control later because if you get stuck in the cycle of Cs for a huge time, there will be an entry which becomes very big. And if this happens asymptotically too often, you will not be Diophantine, okay? But I mean, but it's not immediately clear how to read it. Okay, so partial quotients, or which are AK, become just exactly the matrices B and K minus 1 and K. And the denominators, the convergence, sorry, the denominators of convergence, denominators of convergence, QK, they become the matrix B0 and K. Okay? So that's a dictionary to keep in mind. Okay, now with this dictionary in mind, and with all these preliminaries, first of all, I want to state your cost generalization of Poincaré theorem. So, and then I want to tell you what is the class of Diophantine integral change transformations we handle. I mean, with Giovanni and Matteos. I'm sorry. So I have to get it down until it gets up again, right? Okay. So the generalization, your cost generalization of Poincaré theorem is simply that if you have an irrational generalized interval exchange transformation and the standard one, they are semi-conjugated. There is a semi-conjugacy. So this is if E and T naught have the same rotation number, i.e. The same infinite complete path in the Z diagram, then there exists H, which is a semi-conjugacy, so it's continuous, monotone, and non-two. Such that T is semi-conjugated to T naught. So this fixes T naught. Okay. Now the semi-conjugacy, and here you just need T to be a C0 generalized interval. You assume absolutely nothing more than continuity. Now to get to a conjugacy, I will cut the story. I mean, there are examples of wandering intervals. There is a lot of people who have been working on this. Even, I mean, several people also in the room. So, I mean, I skip on this. But you need, in order to get a conjugacy, also on the circle is known that you need some regularity and some arithmetical properties on the rotation number. You need more. So, and so let me now define, so definition, so because I'm a little bit late, we fix eta to be greater or equal than 0, theta to be less than 1 and positive, and sigma to be positive. And we say that a standard interval exchange transformation T naught is Diophantine of type dC0, sorry, eta, theta, sigma, if the following properties are satisfied. So if we were on the circle, we would only need this one, because on the circle everything is much simpler. And this is what basically you expect. It only will depend on the first. It's that the partial quotients are big O of epsilon of the norm of B 0 and K eta plus epsilon for all epsilon positive. Okay? So I don't know how, I hope you remember, but of course, I mean that, but this is exactly, well, this is like saying that you are Diophantine of exponent eta plus epsilon for positive epsilon. If you choose epsilon equal to 0, then you get Roth type in D equal to 2, okay, for the circle case. Okay. Now, something more is needed. Basically, other three properties. Sometimes the third can be omitted, but not the other two. The second, well, okay, very quickly. All the work we did wouldn't have been possible without Giovanni's work in Giovanni's PhD thesis on the cohomological equation for translation flows. So Giovanni discovered how to solve it, and he showed that that solving the cohomological equation on translation for translation flows requires more codimension than what you get on the torus. So it requires the fact that the datum has to be in the kernel of a certain number of invariant distributions. Otherwise, you can't even hope of solving. Here, the same is true, of course. I mean, it can't be different. And you see it somehow becoming very concrete, because the idea is that, I completely forgot to say, but I mean, there is an obvious candidate solution of the cohomological equation, which is just summing up along the orbit your datum. So if this sum, this formal solution, if it exists, it's actually a good solution. And, but in order to exist, it has to be at least bounded. So what happens is that you need, on the circle, this means that you need a datum which has no average, because otherwise you are adding up a constant. Here you need to kill all the possible components of your datum on the unstable directions of this cocycle, which I forgot to mention is also, these matrices are called, of course, no mystery, Kontsevich-Doric cocycle. Okay, I'm sorry. I just went to the math forgetting all the names. And so the second condition you ask is basically that you have a spectral gap, which will be absolutely necessary in order to build the analog of the invariant distributions to solve the cohomological equation. So this is the spectral gap condition. Okay, so the norm of B0 and K restricted to the space. So these are zero mean piecewise constant functions. Is big O of the norm of B0 and K 1 minus theta. There is a third condition, which we call coherence, which has to do with the action of B and B minus 1 on quotient spaces relative to the boundary. But I don't want to get at all into this because there is no. Then there is a fourth condition, which is characterizing this definition relative to what we did. This definition is in the paper with Matteus and Giovanni, and was somehow motivated also by the desire of looking at the problem of conjugacy in cases where the interval exchange transformation comes from symmetric surfaces where some of the Kontsevich-Doric cocycle is not hyperbolic. So this has to do exactly with the fact that if the dimension of the stable space, which is exactly the space of vectors such that the norm of B, 0, and K, V is big O of B0, sorry, B0 n. Minus sigma. So this is for all n positive. If this dimension is less than G, which corresponds exactly to the non-hyperbolic case, then what you ask is simply that the vectors are not collapsed. Okay, for all, yes, and for all n. Okay, so I think I have 1 minute. 3 minutes. 3 minutes. Yeah. I can state. We can. I can at least state directly the what we proved. Okay, so just in 30 seconds, in 2005, we introduced Ross type IETs with Moussa and Yokos for solving the cohomological equation. And this corresponds to taking eta equal to 0 and assuming only 1, 2, and 3. Okay? And in this case, you can show that you can solve the cohomological equation up to a correction of your datum if you start from a function which is C1 plus bounded variation, a correction which is just a piecewise constant function with a solution which is continuous. And then, of course, you can propagate to higher regularity by assuming better corrections. And this just assumes Ross type. And we also prove that this set is of full measure. Which is a result which can be now derived more elegantly using the work of Avila, Guzel, Yokos on the mixing of the Tushman flow. Then, in 2012, we introduced what is called restricted Ross type, which is still with zeta equal to 0, and you assume 1, 2, and 3. and then and the hyperbolicity of kz. And then and with this we prove a local linearization theorem. In the sense that we prove that, which will be included in the theorem I'm about to state. Okay, so this is now the theorem, and this is okay. Mateus. So if you assume if you take T naught, C, eta, theta, sigma, and I call it near Roth, in the sense that you have a restriction. You cannot take whatever you want. Okay? So you have to take, which includes Roth, but I mean you have to take basically d plus d minus 1 over sigma times d eta, is it d? 4, sorry, no. Less than theta. So this is related to the second exponent of the conservative cycle, and this is related to the least of the positive ones. And so there is clearly some neighborhood, and eta equal to 0 would be the case Roth. So for Roth, this is always true. Okay, so you're just finding a little neighborhood in the space of, rotation numbers of the Roth kind. Of course, a neighborhood which has 0 measure, but still, I mean, not totally trivial. So if T naught is near Roth, then I go directly to the nonlinear statement. The local and you assume and you assume R to be at least 3, then the local CR conjugacy class of T naught is a SIB1 submanifold of codimension d star, which is 2R plus 1 G minus 1 plus S minus mu. So in a second I say what all this among inside the space of CR plus 3 simple deformations of T naught. So the idea is that you have T naught and you look at generalized maps which are obtained by perturbing translation CR plus 3 but keeping the endpoints of each subinterval fixed. Okay? So this is your space. Well, inside this space you have a C1 submanifold of a certain codimension, which in the case of restricted Roth type of hyperbolicity of the conservative historical cycle would just be this, where G is the genus, R here is just the differentiability, it's at least 3, and S is the number of singularities. However, in the case we wanted to treat, because all this work was actually prompted by a question of Krikorian on the ornithorynque and the Volmil-Shao on the codimension in those cases, in the case you don't have hyperbolicity, you are subtracting mu, which is the dimension of the stable space. Okay. I'm sorry, it was a little bit long. Thank you. Okay.